Transformations. The graph of a function can be transformed either by shifting, stretching or shrinking, or through reflection. The elementary transformations of a function f are captured in function notation as follows. For translations, when shifting up or down, we have f of x plus k. When shifting left or right, we have f of and then x minus h in parentheses. For distortion, if you're stretching or shrinking vertically, it's given by a times f of x. If you're stretching or shrinking horizontally, it's given by f of b times x in parentheses. For reflection, when reflecting over the x-axis, we have negative times f of x. If we're reflecting over the y-axis, we have f of negative x. When shifting the graph of a function f of x up or down, it's given by f of x plus k and is called a vertical translation. If k is greater than 0, then the graph of f of x shifts up k units. If k is less than 0, then the graph of f of x shifts down k units. Consider f of x being x squared, this blue function down here. G of x is equal to f of x plus 2, which would be equal to x squared plus 2. Notice how it shifts up 2 units. And we have h of x is equal to f of x minus 3, or x squared minus 3. Notice how it shifted down 3 units from the original function f's vertex. Shifting the graph of a function f of x left or right is given by f of and then in parentheses x minus h, and this is called a horizontal translation. If h is greater than 0, then the graph will shift to the right h units. If h is less than 0, then the graph of f of x will shift to the left h units. Notice here how the original symbol in between the x and h is a minus sign. So let's actually consider some transformations that we have here. And I'm going to come back to this minus symbol in here and how it relates to the movement of the graphs as we examine them. First, we have f of x being equal to x squared, the main parabola that we have. And we have two of its transformations. G of x is equal to f of, and then in parentheses, x plus 2. That's equivalent to f of x minus negative 2. Notice how g shifted to the left 2 units. It's because that minus a negative, which makes a plus sign here, is why it shifts to the left 2. And then for h of x, we have f of x minus 3. So we went 1, 2, 3 units to the right because 3 is a positive number. So again, the graph of g of x is the result when f of x moves to the left 2 units because minus a negative is equivalent to adding a positive. And the graph of h of x is the result when f of x moves to the right 3 units. Sometimes we can have translations that show both a left and right movement as well as an up and down movement. The translation of the graph of a function f of x is given by f of and then in parentheses x minus h plus k. This includes shifting both up and down from the k value as well as left and right from the h value. So consider f of x is equal to x squared, our main basic quadratic function. And we have g of x being equal to f of, and in parentheses, x plus 2, and then plus 1. Notice how g of x is the result of moving f of x to the left 2 units, or going 2 in the negative direction. Remember, we have minus negative 2, which is why it became a plus 2. And then we have 1 unit up, plus 1. So left 2, up 1. That's how we got to g of x. And then we have h of x is equal to f of, and then in parentheses, x minus 3, minus 1. The graph of h of x is the result of moving f of x to the right 3 units and down 1 unit. Now let's talk about reflections. Reflecting the graph of f of x across the x-axis is given by negative times f of x. So if we had f of x being equal to the quantity x minus 2 squared, and we reflect it across the x-axis, g of x, which is the negative of f of x, would be equal to the negative of x minus 2 in parentheses quantity squared. And then if we're reflecting across the y-axis, it is given by f of negative x. So again, if f of x is equal to the quantity x minus 2 squared, and we reflect it over the y-axis, we put a negative only in front of the x. So it's negative x minus 2, and that in parentheses squared, which is equal to x plus 2 quantity squared. Stretching the graph of f of x vertically away from the x-axis is given by a times f of x provided that a is greater than 1. This causes f of x to stretch away from the x-axis and become longer up and down. Consider the function f of x equals x squared and one of its transformations, g of x, being equal to 2 times f of x. Well, we can see how the graph of g of x, it becomes thinner as f of x gets stretched away from the x-axis or vertically upward by a factor of 2. Shrinking the graph of f of x vertically towards the x-axis is given by a times f of x, provided that a falls between 0 and 1. This causes f of x to shrink towards the x-axis by that factor of a. So if we started off with f of x being equal to x squared, your regular parabola, and then we multiplied f of x by 1/2, or 5/10, then the graph moves towards the x-axis or shrinks vertically by a factor of 5/10, or 1/2. Now let's talk about horizontal stretches and shrinks. Stretching the graph of f of x horizontally away from the y-axis is given by f of b times x in parentheses, provided that b falls between 0 and 1. This stretches the graph of f of x away from the y-axis by the scalar of 1 divided by b. So consider f of x being equal to x squared and its transformation h of x being equal to f of 5/10 times x in parentheses. Well, the graph of h of x is the result of that. You are stretching it away by a scalar of 1 divided by 0.5, which is equal to 10 over 5, which is 2. You're stretching it away from the y-axis. Shrinking the graph of f of x horizontally towards the y-axis is given by f of b times x in parentheses, provided that b is greater than 1. F of x shrinks toward the y-axis by a scalar of 1 divided by b. So if we consider the function f of x being equal to x squared and the transformation g of x being f of 2 times x, the graph of g of x shrinks towards the y-axis by a scalar of 1 divided by b, which is 2. So the scalar for this horizontal shrink is 1/2. Use the function f of x, which is equal to x squared minus 1 for each problem below. Write the ruler formula for the new function after the transformations. Okay, so our first one that we have here is 3 times f of, and then in parentheses, x plus 4. So we are going to place a 3 outside of our entire function, and then whenever an x occurs, we're going to substitute x plus 4 in its place. So we have x plus 4 squared minus 1. And remember, this 3 is being multiplied by the entire function. That's why I have this extra set of parentheses here. And if we were to simplify this, we would first distribute the 3 to both this term and this term. So it can be rewritten as 3 times x plus 4 quantity squared minus 3. And this is one way that you can write 3 times f of x plus 4. All right, now let's look at the next one. So wherever an x occurs, we are going to put 5x minus 3 in its place, and then we have to put a plus 2 at the end. So we have 5x minus 3 quantity squared minus 1, and then the plus 2. Now these two constants at the end, we can combine them together, and that gives us 5x minus 3 quantity squared plus 1 as one rule or formula for the new function. Now our last one, we have 1/2 times f of x minus 5 minus 4. So we have 1/2, and we're going to have to multiply our entire function with an x minus 5 in there. So we'll have x minus 5 squared, and then minus 1, and then we have the minus 4 being outside. And we next need to distribute this 1/2 through to both the x minus 5 squared and the minus 1. So we're going to have 1/2 times x minus 5 squared, and then minus 1/2, and then minus 4. And now we can combine our like terms. We have 1/2 x minus 5 squared minus 4.5, or 4 5/10 as a decimal. And here are the solutions to those last sets of problems that we had. Now, these solutions are all in standard form, whereas we left them in vertex form. Either set of answers are correct, and if you just left this first one in vertex form, we had the 3 times x plus 4 squared minus 3. For this one, it was 5x minus 3 squared, and then plus 1, that's the vertex form equivalent. And then the last vertex form equivalent of this bottom one was 1/2 times x minus 5 squared minus 4.5. If you do expand these out, you will end up getting these same solutions of what appears in standard form for each of them. Transformations also lead to domain restrictions. For example, if the domain of f of x is equal to a, which is less than or equal to x, which is less than or equal to b, then the domain of f of k times x will be found by substituting kx in for x in this inequality. So we have a is less than or equal to k times x, which is less than or equal to b. We can also simplify this and divide all 3 of these terms by k. And if we do that, then the new domain for this f of kx will be a divided by k, which is less than or equal to x, which is less than or equal to b divided by k. So what would the domain of g of x capital G of x be if capital G of x is equal to capital F of 5x? Well, we know in this example, the original domain falls between, for f of x, the domain falls between -3 and +5. So for g of x, which is f of 5x, we're going to have -3 is less than or equal to 5x, which is less than or equal to 5. Well, if we want to simplify this, we can divide each and every term of our inequality by the 5 that is in the middle. So therefore, the domain for g of x can be written as either -3/5 as the lower bound, or its decimal equivalent of 6/10, which is less than or equal to x, which is less than or equal to 1. And here's the solution, and it verifies the solution that we found, that the new domain of g of x is going to be -6/10, which is also equal to -3/5, is less than or equal to x, which is less than or equal to 1. The graph of f of x is shown. Its zeros are -12 and +4. What are the zeros of the function g, given that g of x is equal to f of x divided by 3? Well, this x divided by 3 represents a horizontal stretch. So it is going to pull our function further and further away from the y-axis. So it's going to make our zeros come from -12 out to some smaller negative number. And it's going to pull +4 out to be a bigger number. How can we figure those out? Well, we can use the original zeros that we are provided and the transformation expression to determine the new zeros. So we can take this x divided by 3 and set it equal to -12. And now we can solve for x to determine that new zero, or x-intercept. So we can multiply both sides by 3, and we would get that one of the new zeros is going to be -36. We can also do the same thing with the 4. We can set x divided by 3 equal to +4. And now we can solve this proportion to determine that new zero. And that new zero is going to be +12. And the solution provided here verifies what we found, that since f of -12 and f of 4 are both the original zeros, and f of x divided by 3 is equal to g of x, we can set x divided by 3 equal to each zero and then solve for the new zeros. And our new zeros are -36 and +12. Let f of x equal 8x minus 2x squared. Its graph is shown here to the right. The function g is given by g of x is equal to f of 5/10 times x in parentheses. Carefully sketch the graph of g of x on the grid to the right and label at least 3 points on the graph of g. Well, what we should notice with this function is that we have a 5/10 next to the x. So what that's representing is a horizontal stretch. And the scalar of that horizontal stretch is given by 1 divided by b, or 1 divided by 5/10, which is equal to 10 over 5, which is equal to 2. That means we are going to stretch this function away from the y-axis and make its points move double what they originally are. So for example, this point right here at 4, 0 for the original function will move out to be double what 4 is, which is 8. And this vertex, which is at 2, 8, will get pulled away to make it double out away from the y-axis. So instead of being at 2, 8, it'll be at 4, 8. This is 8, 0. And now because this x-intercept at 0 is touching the y-axis, it's going to stay on the y-axis. It cannot be pulled away from it. So this will remain the same. So our new function will look something like this. And it does say to use 3 points. There are 3 points. And now let's write a formula for g that does not involve f. So g of x is f of 5/10 times x. So wherever an x is in the original function, we're going to substitute 5/10 x in for it. So g of x is equal to 8 times 5/10 or 1/2 times x, and then minus 2, and then 5/10 x squared. And then if we multiply these together, we get a 4x here, minus 2 times, well, 1/2 squared is a quarter. So I'm going to write that as a fraction because it's a little easier to deal with fractions when you have to multiply. And we still have an x squared there. And then if we multiply 2 and 1/4 together, we get a 1/2 x squared. And we still have the 4x that's at the beginning. And if we wanted to, now that we have the formula for g that does not involve f, we could factor this in order to find its x-intercepts or verify that they are 0 and 8. Let's actually do that really quick. So I can factor an x out of here, and I'm left with 4 minus 1/2 x. So x is either 0 or 4 minus 1/2 x is equal to 0. If we add 1/2 x to the other side, we get that 4 is equal to 1/2 x. So our x value, or other x-intercept, is going to be 8. So that does verify that our two x-intercepts for this quadratic function are the origin and 8, 0. And this slide right here verifies the solutions that we found. We found that the graph of g is a parabola that was horizontally stretched by a factor of 2, and g of x, the function for it, is equal to 4x minus 1/2 x squared. Let f of x be equal to 6x minus x squared. The functions g and h are given by g of x being equal to negative times f of x, and h of x being equal to f of negative x. Sketch the graphs of g of x and h of x on the grid to the right. We already have the function f provided. And then write the formulas for g and h that do not involve the function f. All right, so first, g of x is equal to negative times f of x. What that will do is it will reflect f of x across the x-axis. So if our original vertex in f of x is 3, 9, the graph of the new vertex of g of x will be 3, -9. And then the zeros will end up staying the same at 6 and 0. And then if we were to connect these to get what g of x is, it would look something like this. All right, and now we have to do h of x. H of x is equal to f of -x. Well, f of -x is going to reflect f of x across the y-axis. So instead of having a vertex at 3, 9, it will be at -3, 9. And then the 0 that occurs at the origin will stay there, but the 0 that occurs at 6, 0 will now occur at -6, 0. So the graph of h of x is going to look something like this. And now let's write the formulas for g and h so that they do not involve f of x. So g of x equals negative f of x, which is 6x minus x squared. So we need to take this -1 that's outside the parentheses and distribute it through. So g of x is going to be -6x plus x squared. And then h of x, I'm going to do the work for h of x up here, is equal to f of -x. So wherever an x occurs, I'm going to put -x in that place, minus -x squared. Now some of you might think minus a negative, I have to change it into a plus sign. Well, not yet. You have to do the exponent first. So -x squared is positive x squared. And now we can also multiply 6 times -x and have -6x. So here is the formula for the function h of x. And here are the solutions. The graphs do match what we had on the previous slide, with h of x being still an upside down parabola going through the origin and -6, 0. And its equation is -6x minus x squared. And then the function g of x, it was the negative of the original f of x function. So we switched both signs. So it's -6x plus x squared. And notice it has a plus sign in front of the x squared and it's opening upward. Whereas h of x, it has a negative in front of the x squared and it's still opening downward. Now that you have seen how each transformation is applied separately, consider an equation with multiple transformations. Which one goes first? Does anybody have any thoughts as to how to go about this? Take a moment to pause this video and think about it, and when you're done, unpause it. To combine transformations, use the following order. Do the horizontal shift of h units first. Then do the stretches and shrinks, go horizontally with b and then vertically with a. Then incorporate any reflections that occur with a or b, whether over the y-axis if b is negative, or over the x-axis if a is negative. And lastly, do a vertical shift of k units. You can think of it as working from the inside out, starting with what is inside the parentheses or inside the function. Let f of x be equal to 6x minus x squared. Its graph is displayed here to the right. The function g is given by g of x is equal to negative times f of, and then in parentheses, x plus 3, and then plus 6. Write a formula for g that does not involve f. That's going to be step number 1. Step number 2, carefully sketch the graph of g of x on the grid that's shown, and then we're going to label at least 3 points on that graph. And then we're also going to describe the transformations that map f of x onto g of x. Let's get started. We're going to start by writing the formula for g that does not involve f. So g of x is equal to negative f of x plus 3, in parentheses, plus 6. So first put the negative out in front of everything, and then wherever there's an x in the original function, place an x plus 3 in its spot. So we have 6 times x plus 3 minus x plus 3 quantity squared. Now we can use the distributive property and square x plus 3 squared to get x squared plus 6x plus 9. And then we can distribute this negative through to get 6x plus 18 minus x squared plus minus 6x minus 9. And then we have a plus 6 outside. Next, we're going to distribute this negative through to all terms that are in the parentheses. So we have negative 6x minus 18 plus x squared plus 6x plus 9 plus 6. Now we can combine our like terms. Notice that the negative 6x and the positive 6x cancel each other out. And then we have negative 18 plus 9 is negative 9. Negative 9 plus 6 is negative 3. So we have an x squared and a minus 3 remaining for what g of x is. In order to sketch a graph, we can take our g of x function that we just found, and we can find its vertex. Its vertex ends up being the same as the y-intercept, 0, negative 3. And then we need 1 point to the left and to the right in order to see the pathway of the function. So we have the point, if we put 1 in here, we get 1 squared minus 3, and that gives us negative 2. Similarly, negative 1 squared is positive 1, and positive 1 minus 3 is negative 2. So there are our points, and there's the graph of g of x. The last step was to describe the transformations that map f of x to g of x. Well, you can also get those transformations from the original function provided here. This plus 3 tells us that we are translating left 3 units. And then because the positive 6 is outside of everything else, we always do that vertical shift absolutely last. So that leaves us with a reflection across the x-axis happening second. So first, if we translate it 3 units to the left, we get this green function, parabola. And then when we reflect it about the x-axis, we get a positive parabola. And then last, we vertically shift it up 6 units because that is the last piece or the last operation that happens to the original function. And when we shift it up 6 units, we get from 0, negative 9 to 0, negative 3 as the vertex. Let's try another example. Let f of x be equal to 4x minus x squared. Its graph is displayed over here to the right. The function g is given by g of x is equal to 2 times f of, in parentheses, x plus 1, and then minus 2 at the end. First, write a formula for g that does not involve f. Then carefully sketch the graph of g in the coordinate plane or grid to the right. Label at least 3 points on the graph of g. And then lastly, describe the transformations that map f of x to g of x. We're going to start with part A. Write the formula or the equation for g that does not involve f. We know that g of x is equal to 2 times f of, in parentheses, x plus 1 minus 2. So wherever an x occurs here, we are going to put an x plus 1 in its place. We have a 2 outside of the whole thing being multiplied by 4 times x plus 1 minus x plus 1 quantity squared. That whole original function is being multiplied by 2, and then the subtraction of 2 that's at the very end occurs last. So if we distribute the 4 through and also multiply x times 1 by itself, we end up getting 4x plus 4 and then minus x squared plus 2x plus 1 in parentheses. Next, we have to distribute this negative through to all 3 terms. We still have, and we're going to distribute the 2 to everything in one step. So we're going to have the 8x plus 8, and then we have a minus 2 times x squared minus 4 times x minus 2 times 1, which is 2, and then another minus 2 at the end. And now if we combine all of our like terms, we get that g of x is equal to negative 2x squared plus 4x plus 4. Once we have the function for g of x being negative 2x squared plus 4x minus 4, we can find the vertex using negative b over 2a. So that would be negative 4 over 2 times negative 2. So the two negatives become a positive, and 4 divided by 4 is 1. That's going to be the x-coordinate of our vertex. And then we need to evaluate f of negative b over 2a to get our y-coordinate. So if we substitute 1 in here, 1 squared is 1 times negative 2 is negative 2. Negative 2 plus 4 is positive 2, plus 4 more is positive 6. That's how we get the vertex of 1, 6. Now, an easy point to find, especially when it's in standard form, is its y-intercept. Substitute 0 in, you get 4. Notice that is 1 point away from the new vertex, so if we go over to the right, instead of 1 unit, that takes us to the axis of symmetry. We can go over another point, and that gives us the symmetric mirror point of 2, 4. You can also substitute 2 in to the function, and you will get 4 as your output for the y-coordinate. Part C is to describe the transformations that map f of x to g of x. Well, we started off down here, and we first moved to the left 1 unit. So we went from here to here, and then we have a vertical stretch away from the x-axis by a factor of 2. So we are pulled up to 1, 8. We went from 2, 4 to 1, 4, and then 1, 4 to 1, 8. And then if we move this entire green parabola down 2 units, we get to our final vertex of our g of x function. So we went through a translation left 1 unit, a vertical stretch with a factor of 2, and then a vertical shift down 2 units to get from f of x to g of x.